All right. Hello, everyone. Welcome to Coinbase Security Session, Episode 8. Thank you for tuning in. I'll be the moderator for this episode. My name is Elias, and I'm on the offensive security team here at Coinbase. Olesa Valanka is a smart contract auditor at Hacken. Today, she's presenting the importance of Web2 security in the Web3 domain, personally one of my favorite topics. If you have any questions, please post them in the chat, and we'll try to get as many as we can towards the end. Please observe the disclaimers that will be on the bottom of the screen. And with that, Elisa, the floor is yours.
Hi, nice to meet you all. I'm going to share my screen, and today we will talk about something that often gets overlooked in Web3 discussions and Web3 security assessments, the Web2 lawyer. So while smart contracts are usually the main focus of audits, many real bugs actually exist outside of the chain. They exist in how off-chain logic interacts with on-chain systems. If this Web2 layer is weak, that contract security may be not enough. And here is what we will cover today. Firstly, we will get some context and understand the main focus of most Web3 security discussions. Then we will look at common failure patterns between Web2 and smart contracts. I will walk you through real-world scenarios and their impact, and later we will see how those issues were actually remediated. And finally, I will give you some practical recommendations, and we will discuss the most interesting takeaways. So in many security assessments, the main focus is on what is deployed on-chain. But a typical Web3 application is not just a smart contract. It's a hybrid of both smart contracts and Web2 components. So Web2 handles authentication, admin panels, business logic, asset indexing, metadata, and so on. And if any of these parts is weak, or if some of those parts are not aligned with the on-chain truths, they can become the entry point for very serious exploits. And based on real audits, there are failure patterns seen over and over again, and they are structural issues in how Web2 communicates with Web3. And today we will go through some of them, not all, but enough to show clear real-world risks. And to make it more practical and interesting, I decided to take real examples from an actual Web3 game where those vulnerabilities were identified and later remediated. So the first pattern is split call workflow. It happens when the business logic is split between two calls. One is on-chain transaction and one is for off-chain API update. And if those two calls are not synchronized, a window opens where the state can diverge. And that's exactly the gap for the attackers. And that's not a smart contract bug, but the system is exploitable. So this is an example of race condition vulnerability. Here is what it looks like in practice. Imagine a Web3 game where there is a flow of NFT importing, where the first step is an NFT minting, and then NFT registration to the Web2 lawyer. And this Web2 lawyer contains a lot of business logic not connected to the Web3. So like some bonuses and things like that, and some gaming stuff. So Web2 lawyer is big enough. So everything starts when user starts an asset import. The on-chain transaction is triggered, and after that, the client calls API to register the token with its owner to update the off-chain state, its DB. But as we see here, there is a gap between those calls. And this gap is unsynchronized window where state may diverge. The owner may change here, but the backend will know nothing about that. And here is how an attacker can abuse this gap. This is the same scenario, but we have not a usual user, but an attacker. So attacker calls mint, then there is a call to the API, and here is a gap. But an attacker between those two calls sells this NFT. So they are not owner of this NFT anymore. They get some profit from it, some funds, some bonuses, etc. But backend accepts this attacker address as an owner and asserts it to the database. So attacker is stored as the owner of chain, while they doesn't own this NFT on chain. And here why it works. The backend simply takes what client sent to it because it's like a single flow, just two-step flow, and it trusts it. But there is no check against the on-chain state, which may differ already. Here is where the problem starts. Here there is a vulnerable backend code. The backend fully trusts the owner field provided by the client here. And there is no check against the on-chain state and no lock-in mechanism. And even if this route is protected, is access controlled, it doesn't eliminate the gap between on-chain and off-chain calls. Essentially, the initial NFT owner becomes the owner in the backend, and this creates a race window between minting and registration that the attacker can easily exploit. To break it down, the backend trusted the owner address sent by the client. There was no check for the on-chain ownership, and any address was able to abuse this NFT ownership during this gap. This is a Web2 and Web3 trust boundary failure. The impact here is actually huge because NFTs can be imported without real owner consent, and the database stores the attacker as an NFT owner, allowing them to use it as own token, and real owner is blocked from using this token. So the state in product becomes inconsistent, and it leads to the broad fairness, and the attacker may gain some bonuses, and depending on the game state. So the contract was not broken, but the system was. Let's look at how this was fixed. Here is the original vulnerable code again. Our goal is to remove this trust in client input and to close this window, to close this race window between on-chain and off-chain state. So we need to synchronize those two steps. This fix moves this registration logic from the client call to the trusted worker. Instead of the client calling the API directly, the backend listens to an on-chain events. So once the event is confirmed on-chain, the worker queries the actual owner, and only after this registers it internally and asserts it to the database. That means that ownership now is derived from the blockchain, not the user. Here is the pseudocode for this worker. We wait for some amount of confirmations. We listen to the mint events, and we perform double check. And only after this, we do the internal assert. But another important thing here that we need to handle block finalization and potential chain reorgs, because events may be not valid yet, and different networks have different finality guarantees. So the API we develop should be aware of that and only trust the state after it's fully finalized. So this worker approach hardens this bridge between Web2 and Web3, ensures backend state reflects on-chain truth. So very often applications break a single logical action into several steps. This creates a timing gap, which may be abused by the attacker in case the backend or frontend is slow. So Our goal is to minimize these multi-step flows wherever possible, to combine on-chain and off-chain in one step. Off-chain updates should always be triggered from on-chain events, not client actions or not manual user actions. So we need to make sure that system also accounts for block finalization to ensure that we track for correct events. And we need to remember that we need to set it up differently for each network because different networks finalize blocks differently. We should never trust front-end timing. We need to revalidate state on action. We need to call smart contract again each time we do any sensitive operation. And if the off-chain state hasn't synced yet with the chain, it's better to block the action because it's better to have a failed transaction or failed action than an exploitable gap. The second scenario is a more subtle, but still very common. Problem here is also in hybrid Web2, Web3 systems, but it's not about an attacker racing the system. It's about the system drifting away from the chain itself. So whenever a product keeps asset state both on-chain and off-chain, cache or database, and this synchronization is delayed or unreliable, it creates what we call a drift zone. Even valid transfers can result in stale ownership or stale permissions because the backend no longer reflects the actual blockchain reality. This is the kind of code that causes it. This endpoint checks the ownership against the database only. Here, there is no on-chain verification. So in case database is out of sync, the product just believe it, and ownership check is not correct here. The consequences can be really serious here. It may lead to the host ownership. It may block correct users from actions they should be allowed to, and the product will end up in a broken UX state, often needing manual fixes. And this is exactly the kind of bug that slipped through functional testing but hits production hard. Here is the example of such a bug. For example, user A transfers NFT to user B on-chain. So on-chain owner is changed, but our cache is not updated yet. So backend still assumes that user A is an owner, though user B is already an owner. That means that user A can keep performing off-chain actions they shouldn't be allowed to. So it even was not an attacker exploiting a bug, but it was a valid user who just unintentionally exploited this weak design. Let's fix it. The core problem was not the transfer itself. It's the trust in stale data here. So just like in the first case, the fix is to trust the chain, not the cache. And what is interesting here is that the fix here may actually be the same as in the first case, but we can use this similarity to our advantage to dive a little deeper to understand how to design the fix properly. And once we get this pattern right, it may solve multiple classes of issues at once. The first step is to introduce an event-driven worker, just like in the first pattern. When a transfer happens, our event, and it is confirmed, event listener verifies the owner from the smart contract and updates the internal state. This keeps the backend state tightly coupled to the blockchain. And here is the pseudocode for that. We listen to the transfer event, verify ownership, and do internal syncs. Again, we need to make sure that the system accounts for block finalization. Here we do it, but we don't see the code because for each network it should be done differently. So this fix removes user input from the quotation and eliminates stale state at the source. The second step is also very important. we shouldn't believe that we track everything. Even if we listen to all the events, we cannot rely on the cache or database. We need to recheck. Ownership at each sensitive action. So we need to call owner of token ID, and based on this, we need to decide whether we need to allow or deny it based on the on-chain information. So whenever a critical action happens, like in our game, use NFT, we need to recheck, revalidate the data on-chain. So here, even if we listen to the event, we still call contract owner off and we revalidate if. This step without the first one doesn't fully eliminate the drift, but it prevents stale state from being exploitable. So the first step, implementing the worker, helps us to keep the data consistent and to show consistent data, to store consistent data. But this step protects the system from really using incorrect data. So it is a two-step protection. A lot of projects keep part of their logic both on-chain and off-chain. For example, ownership or pricing on the blockchain, but metadata or user state in a database. And when these sources are not perfectly aligned, attackers can take advantage of the gap, just like we saw before. So the first rule is to have a single source of truth for all critical checks. And this source of truth is blockchain and on-chain part. The database should only mirror what's already on-chain, not override it. Secondly, we need to rely on event listeners and trusted workers to front-end input. So this will prevent from indicating the incorrect data. Third, for each sensitive action, like transfers or trades, we need to recheck the actual state from the chain in real time. This will prevent users from using the incorrect data. And finally, as a good security practice, the drift monitoring should be set up. So from time to time, reconcile the database with the on-chain state. This will prevent silent inconsistencies from becoming exploitable bugs. The third case is one of the most common architectural weaknesses we see in hybrid Web2 and Web3 systems. And we even often see this in smart contract audits. Here, it's not a bug in the contract, it's a gap between where business rules live and where they are actually enforced. This is the most simple case. This one is the most simple case, but also critical. In this setup, the critical rules live only in the backend. The contract trusts anything that passed to it, assuming that the backend will always act as a gatekeeper. But attackers, as we know, can just keep the gatekeeper and talk to the contract directly. So as a result, the contract executes with completely unverified parameters. Let's move to a more interesting example. This is a classic example of what happens when business logic is enforced inconsistently between off-chain and on-chain lawyers. Here, the backend and front-end enforce a price limit of 100, but a smart contract has no or weak enforcement. The UI displays the expected value, but an attacker ignores the front end completely, calls the contract directly, and uses a much lower value. Because the contract doesn't enforce the same business rule, then transaction goes through, and that's how attackers exploit the weaker enforcement layer. So as a result, the backend and contract states diverge, business rules break, and the system may end up with corrupted listings or stolen value. In case limits in the backend are stricter than in smart contracts, this may lead to the broken UI, UX, and to the failed transactions. Here is what happens when the backend assumes it's a source of truth. It enforces its own limit, 100, but the contract doesn't necessarily follow the same rule. So this works fine if everyone uses the front end, but attackers may not use it. So on chain, the contract has a different limit. Or none at all. The attacker just ignores the backend and calls the contract directly, minted 1000 instead of 100. So the backend thinks everything is under control, but the contract accepts the transaction. This gap between off-chain and on-chain enforcement creates multiple attack surfaces. Firstly, hackers can completely bypass backend checks. Secondly, they can manipulate supply or other critical values directly through the contract. This may lead to the broken transactions in case backend implements those rules incorrectly, in case those rules are more strict in the backend side. Also, this may lead to the broken business invariance because in case rules enforced off-chain are not guaranteed on-chain, this fully breaks the system. Here is the secure version. Here is a secure version of the contract. We just ensure that limit is the same as in the backend. And we ensure that smart contract implements the same business logic and limit as a backend. The remediation principles are like this. Web2, Web3 systems should have single source of truth, the chain or cryptographically signed messages. Backend rules should either mirror directly the smart contract rules or just create signed messages which will be verified on chain. And there shouldn't be no divergence between backend rules and on-chain rules. So in many hybrid systems, the weakest point isn't the smart contract. It's a Web2 lawyer that connects to it. Teams build strong backend, enforce limits, validate inputs. But if this logic is not cryptographically tied to the contract, it's just a suggestion, not a rule, because it can be easily bypassed. So once somebody bypasses the Web2 lawyer, the contract will trust whatever comes in, and that's where things break. So the first rule here is on-chain rule enforcement. All the critical rules should be enforced on-chain. In case logic has to remain off-chain for business reasons, cryptographic signing should be used and contract should verify it. And this cryptographic should be implemented correctly as well. And finally, rule alignment should be strictly followed. We need to make sure that Web2 and Web3 use the same data models and limits. And as the last good security practice, test for drift should be done by time by time. So we should compare backend and contract enforcement paths. We should validate whether all the limits and rules are the same. To wrap this all up, even if the core logic lives fully on-chain, Web2 remains the main attack surface in hybrid systems. Most of the real exploits we see today happen because backend or off-chain logic can be bypassed. Every critical check must either live on-chain or be cryptographically verifiable. Anything else can be forged. Also, good old Web2 security practices don't disappear in Web3. Authentication, input validation, login, monitoring, they all matter. And finally, test both Web2 and Web3 together. Compare backend and on-chain enforcement paths to make sure there is no divergence, because in the end, most vulnerabilities are not in the blockchain itself, but in the bridge between Web2 and Web3. Thank you for attention.
Amazing. Cool. It looks like there was One question that came in, so I think we can start with that. They're basically wondering if removing the transfer function makes the SP token fully safe, or if there are other ways people could try and game or exploit it. Um, the question itself, are there any specific checks or attack vectors to consider for non-transferable fungible tokens that are being used as XP within our ecosystem? He removed the transfer function, but wanted to better understand if there's anything specific they should check or be on the lookout for.
Oh, even in case transfer is removed, we cannot rely that the owner is not changed because the contracts may be upgradable and on-chain is not state unchangeable. We still need to verify the owner of the NFT token, and even if we do not listen to events, because this may waste our resources, because transfer is removed, we need to verify the owner for each critical operation, and that's the main rule, because the main rule of Web2 and Web3 secure integration is the single source of truth, which is on-chain part. So I believe that's the main rule for this.
Cool. With a focus on you people coming into Web3, what are the best tools that you would recommend people use?
Oh, that's interesting. I would recommend using just some code editor and to try to implement some smart contracts by themselves, some simple tokens. And for the first tries, some remix can be used to try to call those functions to see how state changes. And after that, we can go to the foundry, to the hard hat, and to try to create some coverage. So, and basically that should cover all the initial stuff.
Nice. How can organizations effectively train their Web2 security teams to identify and address these Web3 specific or cross collaboration vulnerabilities that they were talking about?
Yeah. As always, organizations should provide this security training, and regarding Web3 security, those sessions should be provided as well. And smart contract risks should be discussed there, and very important, very often discussed, but still private key management should be discussed. And because as far as we know, a lot of exploits happen because of weak private key management, and also trust boundaries between on-chain and off-chain components should be discussed. And also, when doing Web3 audits, it is good for the whole team participating in it. So, like when they do the audit, then the whole team can read the audit report, and then they will understand better what are the main risks.
Amazing. What is the most effective strategies for fostering collaboration between Web2 and Web3 development teams to improve the overall security posture?
Probably the most important thing, because everything starts with the design creation, and in case design is wrong, this may lead to the issues later. So when the design is created, there should be shared security ownership involving both Web2 and Web3 teams. So they will create common documentation, common security standard, and security communication channels to bridge knowledge gaps. Each team will share knowledge about risks, and then the design of both will ensure that the communication between those parts is good. Sometimes there are some tools which can be shared, and as in the previous question, training sessions can be done for both teams together.
How can incident response plans be adapted to effectively address security breaches that span both Web2 and Web3 components?
There should be defined steps. For example, key revocation in case of exploit or incident, some smart contract pausing or emergency withdrawal, depending on the smart contract, or some other on-chain steps into a traditional Web2 incident playbook. So those steps should be connected and they should be done together. So ensure joint response teams are trained to coordinate across centralized infrastructure and decentralized components in real time.
Perfect. I think that's all the questions we had. I'll give it maybe 3 more seconds of just awkward silence just to see if anything quickly comes in. But thank you. Thank you for joining today's session. Alicia, thank you for your time presenting here. In 2 weeks, we will also have the 9th episode where Opal from BlockSec will be presenting approaching secure signature validation in smart contracts. Going once, I'm not seeing anything new coming in. So thank you guys, everyone, for tuning in, and have a great rest of your day.